Good afternoon. Welcome to today's NITheCS Colloquium. I'm Anselm John from the Department of Physics at Stellenbosch, filling in for Francesco Petriccioni, the director of NITheCS, who is away today. It gives me great pleasure to introduce today's speaker, Professor Romeel Davé. Professor Davé holds a position at the School of Physics and Astronomy at the University of Edinburgh. And prior to that, he held a Saatchi chair in cosmology based jointly at the University of the Western Cape, as well as the African Institute for Mathematical Sciences and the South African Astronomical Observatory. Professor Davé obtained his PhD from the University of California and went on to hold a number of postdoctoral fellowships at places like Princeton University and the Stewart Observatory. He is a computational cosmologist who uses high-performance computing to study black holes, galaxies, and the universe. And we're really looking forward to his talk today. You might be aware that Professor Davé is also a known science popularizer and has recently published a book titled Simulating the Cosmos, released last year. So without further ado, I hand you over to our speaker.
Awesome. Thanks very much, Anselm. Thank you to Francesco and Absentia and Renee and everyone organizing this wonderful series of talks, and for inviting me to present today to you on some of our work. So, see if I can find the pointer. There it is. So, yeah, as Professor John mentioned, I do numerical cosmology. So essentially, I try to put the universe into a computer. And today, I hope to give you a little bit of a flavor for how we go about doing this, why we go about doing this, and also, what are some of the cool, interesting things that we've learned. You might think, well, it's a computer. You put in what you get out what you put in, right? How do you learn anything from that? Well, it turns out you can learn quite a lot, and to give you a flavor for some of that today. Okay, so starting from the very sort of biggest picture, right? What are we trying to do here? So the goal of this, in a very broad sort of humanistic sense, is answering the following question. Where did it all come from, right? And this is a question that's been present throughout the history of humankind. It's something that there's been, generally, historically, this has been the purview of mythology or religion, where the cosmos was originated, these sorts of things. There are, many fables from every culture has pretty much a fable of how objects in the sky, constellations or features in the sky come about. So this is all sort of well and good, and it's great to to study those and to get a view into the sort of cultures that have come before us. On the other hand, those sort of stories are lacking one crucial ingredient in order to be science, and that is that they are not repeatable. So no one can go check whether something can, create the cosmos when, I don't know, spiders did something or something like that. So instead, we'd like to create, in the interest of having something that is verifiable and that is something that is subject to the testing and hypothesis testing idea of science. We'd like to do something that's a little more scientific. But to do that, we need data. Okay, so the whole crux of the scientific process is that we need to have some observations or some experiments that we're able to do and be able to explore the origin of our universe. And it's for this reason that the science of cosmology really started relatively late. Okay, and it really started in truth in the 1920s. And there's often a lot of credit given to this fellow right here. That's Edwin Hubble, right? That's a familiar name to you, Hubble Space Telescope, etc. But it wasn't really that guy. It was the thing in front of him that was really important. It's a telescope. And at the time, it was the world's largest telescope. And because he had access as a professor at Caltech to the world's largest telescope, which was the 100-inch Hale on Mount Palomar, he could see things that nobody had seen before. And so when Edwin Hubble decided to what should I do with this cool new telescope, he pointed the telescope at these fuzzy blobs in the sky, which no one knew what they were at the time, right? And these fuzzy blobs were, it wasn't clear exactly where they were. So he decided, well, what he'll do is he'll go measure the distance to these objects, right, and see if they're kind of within what we might think of as our own galaxies, similar to stars, or far beyond that. So he decided to measure the distance of these objects using a technique developed about a decade or two earlier by Henrietta Leavitt. And she noticed that there was this particular kind of pulsating star whose period could be linked to the luminosity. And of course, if you know the luminosity and you know the apparent brightness on the sky, you can infer the distance just by the fact that light goes down as 1 over r squared, the intensity, right? So that's how he could get the distance. But he could also get the rate at which it was either moving away or coming towards us. And you could do that by, essentially Doppler shifting, right? So essentially, he can take a spectrum of the galaxy, and then he can compare it to the spectrum of a known set of elements here on Earth. So he looks for the hydrogen lines in that galaxy, compares it to the hydrogen lines we can measure in our lab on Earth, and he notices that the two things are shifted. Now, why would they be shifted? Well, if you imagine, if you think about, let's forget about galaxies and light, think about just an ambulance coming towards you. It has a siren, meow, meow. As it's coming towards you, the siren has a higher pitch, and then it goes by you and it gets a lower pitch. Meow, meow. Why does it do that? Well, it's a Doppler shift, right? And effectively what that is that the sound waves are getting squeezed when the thing's coming towards you and getting sort of stretched when it's going away. Well, light does the exact same thing. So things that are coming towards you will get to a higher frequency, and things that are going away from you will get to a lower frequency. Our eyes interpret frequency of light as color, and it turns out that lower frequency corresponds to redder light, right? So by measuring this red shift of these lines, he can get just the recession velocity, not the velocity in either other transverse direction, but just the long line side. So this was his amazing discovery. He discovered that basically when he plotted those two quantities, what he noticed is that they fell along a straight line. Now, what does that mean? That means that basically if you go out some distance, you will see a typical galaxy is receding away from us everywhere, in every direction we look, right? And then if you go twice that far, it's receding twice as fast. And that's expressed just in this law that we now call the Hubble-Lemaitre law. And that guy is this dude here, because he was the first one to sort of conjecture that he actually, he released his paper in an obscure Belgian journal in French 2 years before Hubble published the data, but he had just gone and seen a talk by Hubble, presented this stuff, and he went, oh, what would be the implication of this sort of configuration? How do you end up with galaxies that would look in every direction, all moving away from us? Well, the idea was that the universe must be expanding, right? And so the whole universe is expanding in every direction, and the inference from that is if you run the clock backwards, you get it back to a very compact state, and that must be the beginning of our universe. And this was a momentous occasion, right? Not only in science, but in philosophy and religion, that the universe was not static and immutable, but rather was changing, had a beginning. And presumably things, changed over time, because obviously, if you put everything in the universe in a very small spot, it must look different than things today. Okay, so that was a big moment, and we had an idea that has been since confirmed by many other measurements, and we'll talk about a few of them later, that we have this Big Bang, and particularly when you compress everything, of course, it's hot, so therefore you have a hot Big Bang. Okay, so now we sort of fast forward a little bit, 100 years later, and we have things like the James Webb Space Telescope, and we can go out and take pictures of the sky and say, what is this Big Bang that occurred? Now we know it's about 13.8 billion years ago, right? what does it look like today? Well, this is a patch of the sky, right? Taken by pointing the Hubble Space Telescope at just one spot and staring for a while. It's a patch of the sky. It's about the size of your fingernail held at arm's length. Okay, so it's a really small patch of the sky. Just about every object you see in here is a galaxy. Okay, so there's literally thousands of them here. You can probably even see with your eye, and there's many more that you can pull out. Screen doesn't really do it justice. So it's really quite remarkable, right? And not only that, you see that these galaxies are all kinds of things going on. It's a little hard to see here, but you see very flat, long cigar-shaped galaxies. You have galaxies that seem to be, have some kind of a bridge between them, so on and so forth. There's different colors. So this is kind of weird, right? Because you started off in this very hot, dense state, and 13.8 billion years later, this is what it is. And in fact, many of these galaxies are actually being seen when they were much earlier in the universe as well. Right? You can see very far back with the JWST. So the point I want to make about this slide is the following. If we want to understand where it all comes from, right? If we want to understand why our universe looks the way it does, we have to understand essentially galaxies, because that is the primary marker by which we see the deep universe, starting from Edwin Hubble, right? So this is the field of galaxy formation, and this is what I work on. Well, probably the largest sort of field, subfield of astronomy today. And the reason for that is because it's extraordinarily complicated. So this is a probably incomplete list of phenomena that are crucially important to forming galaxies, right? So on the very large scales, of course, we have the overall evolution of the universe. The fact that the universe has changed over time must imply something about the formation and evolution of galaxies. That's cosmology. But the light that you see from all these galaxies is predominantly, for the most part, coming from stars. And so we have to know how stars form. Well, that in itself is a pretty complicated problem. Stars just don't form once and not do anything. They eventually die and do crazy things like blow up, go supernovae, right? So we have to worry about that. Those supernovae then scatter heavy elements. Remember the Big Bang, essentially all you have formed at the time of 13.8 billion years ago was essentially hydrogen and helium. And so everything that else that we have for the Earth or whatever is all formed in subsequent stars, right? So we have to understand that. The production of the heavy elements. There's dust in the universe. Nobody cleans out there. It's pretty big. There's dark matter. Of course, we heard from Professor John a couple of weeks ago, I guess, or about various issues around dark matter. We'll talk more about it later. Black holes. About 25, 30 years ago now, we started to realize that every significant galaxy has a huge supermassive black hole in the middle of it. What's that doing? Turns out it does a lot. Okay, another thing we'll talk about a lot. And in general, all of these processes are can release energy. Especially the blowing up of stars or the energy release from the accretion processes onto black holes. They put energy back out. So it's not just a question of galaxies just kind of naturally just forming by themselves and not doing anything. Galaxies themselves do stuff to stuff around it, right? So this is sort of this. We'll talk about this a little bit more. So the point is it's a very complicated set of processes, and this is kind of minimal, right? What I'm showing you here. We can't form realistic looking galaxies, without including at least all of these processes, and there may be more. Okay, so how do we try to tackle this level of complexity? We try to put it on computers, right? Because essentially there's so many things, interrelated things going on that analytic models are, let's just say, limited value, right? They're not no value, but they're of limited value. So how do we go about doing this? Well, the idea of it is so simple that you might wonder what all the fuss is about, right? Why do so many people work on this? So the idea is to put the cosmos into a computer. What we do is we imagine that we have a random chunk of the universe that we just kind of took out of the universe that is large enough that is kind of representative of the whole universe, right? So we have this random chunk of the universe, and the kind of numbers I'm talking about are 100 million light years, few hundred million light years, so huge scales, right? Like millions of times bigger than the distance between, or size of our galaxy or something like that, right? Then in this box, we're going to stick a whole bunch of particles, and each particle is going to represent a chunk of mass. So we're going to represent all the mass that would be in a random chunk of the universe with huge numbers of particles. Now the particles are going to evolve over time. We're going to start the particles in a position that's very early on, very close to the Big Bang. Then what are we going to do? Imagine, so the kind of numbers we're talking about these days are hundreds of millions or billions or sometimes even trillions of particles. But I'm showing here a simulation with 6 particles, just to kind of illustrate what's going on here. So I have 6 particles in one of these boxes. What I can do is, of course, I can calculate the force on every particle from every other particle, and whatever forces I want. Gravitational force, hydrodynamic, any other forces I want, magnetic, if I wanted to. So I calculate all these forces. Then I go to use good old Newton's second law, right? F equals ma, right? So you use F equals ma, then I get the force on the particle. And I know the force, right, is related to the acceleration. Divide by the mass of particle, get the acceleration. Now what I do is I choose a time step. Call that delta t. So that time step, delta t, is going to be how far I'm going to evolve the system as a single step forward in time. So, we're talking there will be at least many thousands or maybe millions of time steps over the course of the whole universe. So it's by cosmic scales, it's a small amount of time. If I have an acceleration and I have a time, you know that acceleration times time is velocity, right? So then I know how much the velocity of each particle changes because of the forces from all the other particles. And similarly, position is velocity times time. So then I can tell how the particles move within that time step delta t. So now I've moved the particles from here to here, right? So all these particles move a tiny little bit, and then I just repeat it, right? Computers are very good at doing these kind of calculations, billions of times without getting bored, right? So we go some big supercomputer, and we throw a gazillion particles into it, and we run this until we've taken enough time steps to go the full 13.8 or whatever billion years of the universe. And we get something out, right? Cool. So why do we do this? What's the point of doing all this simulating, putting all these particles and evolving them? Well, if we can do this, right? If we can do this, this is kind of an amazing platform to study the universe. Now, remember, as astronomers, right, we are in a somewhat unique position in among a lot of physical sciences, really, in that we don't control our experiment, right? The experiment's out there. We can't get to it. We can't tell a star to go stop shining for a bit so we can run some little experiment on it, right? It's an observational science. In this sense, it's more like archaeology than it is like physics or chemistry, where you have a lab where you can carefully control everything and test the one thing you're interested in. So if we can set up one of these fake universes and get, convince ourselves that it's at least realistic enough that it's going to give us some interesting intuition, that's a little bit of a judgment call. But let's say, yields a realistic looking population of galaxies compared to, let's say, like that JWST picture or something like that. Then we can run numerical experiments, because in the simulation, we can tell a star to turn off for a little bit, right? We're the god of our little universe, right? So we can do whatever we want. And then we can understand the impact that new physical process or that new physical experiment will have on, how the system might evolve. So this is how we sort of, have come to this collection of physical processes that we think are important for galaxies. Because if we remove any one of them and say, oh, let's just turn that process off, we just can't get realistic galaxies anymore. So we have to include it. And each time, we get more and more fancy observations from all these, fancy telescopes. Here's MeerKAT and SK over there, JWST, right? All these new telescopes that are coming up, giving fantastic amounts of data. Each time these new telescopes come in, they give all this new data, and the simulations have to understand it. right? The simulations have to interpret those observations. And as powerful as JWST is, or MeerKAT, or whatever, it's only looking in a single region of wavelength space. So things look different in these different wavelengths. So to connect them, simulations provide a good tool for that as well. So it can be used. These simulations are extremely useful in a wide variety of ways, and it's because this field is sort of reached some level of maturity, I guess, in the last 5 or 10 years, that essentially these things are now considered an invaluable part of kind of any large scientific endeavor, right? If you don't include simulations, let's say in your big grant proposal, you're definitely less likely to succeed, right? Because they'll be like, well, what model are you testing, right? So this allows you to do kind of science, like hypothesis testing, which is something we can't really do on the real universe easily. Okay, so if we want to do this, of course, we're going to have to decide a couple of things, right? How do we set up our little simulation box? Well, the first thing we need to do is we're going to have to figure out what these particles actually, what kind of forces these particles are subject to. Okay, so we have to know what the universe is made of, right? That way we can know what kind of particles to put in this box. So that's already, of course, a big field in of itself. But these days, the typical numbers that the typical things that we do is we have this what we call a concordance cosmological model. It's called that because essentially there's a huge number of various observations that all sort of pinpoint to this one model, which is quite a coincidence if it was just random. So instead, we think this is probably some close representation of what the real universe is looking like. So it's made up of 3 main components. The first is the one you're familiar with. It's normal matter. Simulations or astronomers like to call it baryonic matter. It's a misnomer. That's not actually just baryons, for instance. Electrons are called baryonic matter. It's basically, to an astronomer, a baryonic matter is anything that interacts with electromagnetically, right? So it's everything that you see in the periodic table, right? So everything that your chemistry teacher told you makes up all of matter, right? That's only actually 5%. So that's we're in the minority. So and in fact, the stuff that makes up the heavy elements like carbon and oxygen, it's 2% of that. So 98% of that 5% is just in hydrogen and helium. Okay, so if anyone ever tells you you're not part of the 2%, say yes, I am. Okay, right? So so that's the normal matter. That's ordinary matter. About 25-ish% of it is dark matter. We heard about this from Professor John. It's stuff that doesn't interact with light. And there's much evidence at this point. Again, you could give a whole talk about the history of all that. I think the bullet cluster was mentioned, right, as a good test of this, where you clearly see, dark matter and this normal matter, the gas, has been separated out, right? And then there's, of course, all this stuff, about 70%, which is dark energy. So dark energy is yet another misnomer. Astronomy is full of misnomers. It's not really an energy per se, okay? It's best described as a vacuum pressure. That every tiny piece of vacuum, without, you were told that vacuum was empty by your chemistry teacher lied to you straight up, okay? So a vacuum is not empty, okay? A vacuum can have all kinds of things going on. And one of the things going on is that can have an intrinsic pressure associated with it. Einstein's equations of general relativity allow for this, right? And this pressure is extremely tiny on any given piece of vacuum, right? But so it's so tiny that basically, we don't notice it. Anything with any kind of significant gravitational field completely overwhelms this outward pressure. However, once you go between galaxies to huge distances, each bit of vacuum is adding more and more pressure, right? And so over those huge scales, dark energy causes, just like if you push pressure with anything, it will accelerate, and it causes the acceleration of the universe. So, so this is causing the accelerating expansion of the universe. Won the Nobel Prize in 2011 for discovery in 1998. Okay, so that's the ingredients that we need Dark energy affects how fast the universe evolves, doesn't really do much on small scales, but we have to include both dark matter and normal matter. The nice thing about dark matter is, as far as we know, only responds to gravity. So we can at least start with making simulations which include gravity only, and we already learn interesting things. But the second thing that we need to know before we start our simulations is where to start. Okay, I said we start at the Big Bang. Okay, what does that mean? Turns out we actually know this really well. All right, and this is an actual real picture of an observation of our baby universe. There it is, very cute, right? 380,000 years old. Our universe, this is what our universe looked like. This is an all-sky map. You see all these little tiny red and blue spots on these maps? These are temperature fluctuations measured by this satellite that's out, out in space, and they correspond to little cold and hot spots. But these spots, these cold and hot spots, are just tiny variations on a very, very smooth field. So typically, it's less than 1 part in 100,000 in variations. In other words, these variations are, they've been exaggerated for scale on this thing, but they're smoother than the stillest pond you have ever seen in your life. Okay, so these these fluctuations are extremely small at this time, right? But as you'll see, they are the result, they are the cause rather of everything, of the fact why we have galaxies, why we have planets, why we have people, everything. Right? It comes from these fluctuations. And if you really want to know where the fluctuations come from, that's a whole nother story, but I won't get into that. Okay. So we have the initial conditions. So we can take our particles and we can distribute them in our box. We can imagine we have a small box taken out of this map here, and we can distribute our particles such that they reproduce, maybe even at least statistically, the fluctuations in the mass that we see in this box. The temperature, basically, fluctuations corresponding to mass fluctuations. Okay, so that gives us our starting point. We have our ingredients, and we have our methodology. So let's see what it looks like. All right, here come the movies, right? That's what you guys wanted. So this is a movie of a simulation that includes only dark matter and follows only the force of gravity. Okay, so it doesn't include any of the sort of the normal matter, because normal matter, as I'll explain in just a second, does all kinds of much more complicated things. So it's going to start early on. So you see the field is very, very smooth. The mass field is very, very smooth. There's small fluctuations. This is starting probably about 200 million years after the Big Bang. So still well after the cosmic, that picture I showed you. But nonetheless, you can start to see the fluctuations. Okay, so what happens? Whoa. Okay, so it's a little jumpy. Sorry about that. But as you see, what quickly happens is that all the mass collects into these structures, these kind of filamentary sheet-like structures, and then down into these little clumps. And why does it do that? Well, it's something that it's a phenomenon that we're all very familiar with, unfortunately, which is that the rich get richer, right? So you have a little patch of the sky that essentially, because it has a slightly more mass, remember back in the CMB, there's a region that has slightly more mass, even though it's 1 part in, a few parts in a million, it's able to gravitationally attract stuff from around it, grows, then it has more mass, and it grows even faster, then it has more mass, grows even faster. So this is an unstable process. And you can see it operates very, very quickly, right? As soon as you start to go, nonlinear, you very quickly evolve into this highly nonlinear set of structures, right? So 2 things it tells you, right? We can understand now why our picture of James Webb Space Telescope looks so empty, right? Because all the mass has now been, or at least not all of it, but a lot of the mass has been concentrated into these little, particular objects that you're going to see as galaxies, right? The second thing is this idea of a cosmic web, right? So essentially, this pattern that we see is dependent on the parameters that we put in, on the amount of dark matter, dark energy, etc., right? And because of that, we can go out and measure galaxies in the real universe and measure their patterns on the sky and compare that to these kind of simulations, and from that infer how much dark matter and dark energy. That's one of the ways that we actually measure those quantities that I just kind of rattled off, right? Okay, so that's an example of a dark matter only simulation. But of course, galaxies are not, or at least the part we see, are not made of dark matter. Nothing that we see is made of dark matter. It's dark, right? It doesn't interact with light. So if we want to model galaxies, we're going to have to deal with the normal matter. And it's only 5% of the matter, but it's like 99% of the work. Okay, it's a pain in the freaking keister. Okay, so why is that? Because the baryonic matter can do all kinds of other things besides just be attracted by gravity, right? Of course, it has gravity as well, but it also undergoes heating and cooling, right? Gas could be hot or cold. It can form into from hydrogen and helium into other elements. It can have pressure, do all kinds of things, right? So to track all that, we have to have more force terms. And this is what's called hydrodynamic simulations. So this is called, now we have a cosmological hydrodynamic simulations. So I'm going to show you an example of one of those. And particularly it's from the illustrious TNG group. And what I'm going to show you is 4 panels. It's the same simulation. We're just looking at a different quantity in each panel as it'll evolve from very early on to today, okay? So on the left panel, it's going to be the stars. This is in the very early universe where we're starting, so there's no stars yet. Gas, of course, very smooth. The temperature is all very cold right now because there's nothing to heat it really, and there's no heavy elements formed because there's no stars, right? Okay, so let's see what happens. So as we start to go down in the simulation, we're now at maybe 500, 600 million years after the Big Bang. You start to see. Oh, and one more thing I should mention, right? This is all. We've taken out the expansion of the universe here. So we're sort of just looking in this frame called co-moving coordinates. So already, in the first billion years, we're still not even a billion years into the universe. We're starting to form a few stars. They're forming along these filaments, right? These cosmic web filaments that I just showed you, forming due to the gravity. The stars are creating these heavy elements. So there's little patches of heavy elements being blown around by the supernovae here. And they're heating the gas because, of course, as you compress things, it heats up. So you get little hotter regions here. You'll start to see we're still only about 2 billion years into the evolution, 2.5 billion. You start to see some of these supernovae heating up. Look at this little flickering. I don't know how well you can see it, but we have these sort of little explosions. This is the black holes. So they've included black holes in these simulations too. And these black holes are really energetic and they can really kind of go off, right? Look at that one. Whew. All right, it's starting to really get as these black holes get bigger and bigger, you really start to right there it is. So and you see they're distributing all these heavy elements everywhere, right? But look at the stars, right? You wouldn't tell looking at this. You say, oh, look, there's just a few galaxies here. There's a whole bunch of empty space. No, look at all that, right? It's crazy what's going on. It's just we don't see this stuff, right? We see the stars. Those are the things that shine, right? So this is, a simulation. Now we're sort of, about almost 10 billion years into the cosmic time. You see there's huge numbers of galaxies that are being formed. They're in these kind of filamentary structures. The universe has been heated quite a lot. There's heavy elements everywhere. And these stars, you notice the colors of these stars, these have turned redder. I'll explain what that means in a little minute. But that's realistic. This is like what you would see with your eye. So that's an example of how, how we can model, the full hydrodynamic simulation, right? In fact, there are a lot of these now. The illustrious TNG is far from the only one that's doing this kind of work. They just happen to make the best movies. And there's other ones like Eagle, or this is mine over here, Simba. So we're including again all of these processes that are these sort of minimal set of processes that lead to galaxies. But there are other processes that people may think about. Magnetic fields people have started to look into, radiative transport, cosmic rays, all these other things that you could potentially include, but most of them don't have it. Nonetheless, you know, there's tons of these groups now doing these kinds of simulations. And you might ask, why? Why bother? Like, it's done, right? You know, why do so many different ones? Well, I just want to give you, instead of sort of explaining it to you, I'll show you in a movie, because that's what this talk is about. Okay, so what this is going to show you is a movie from the CAMELS project. CAMELS project is a set of thousands of these types of simulations done with many different codes, but essentially for machine learning training purposes. So we're using a lot of machine learning with this. But it's, now what's being shown here, there's going to be 4 simulation panels. It's the exact same simulation, but now it's run with 4 different of these different kinds of simulation codes, right? So this one is going to be Illustrious CNG, this is mine, Simba, and these are 2 others, Astrid and Magneticum. Okay. Fair enough. So what's shown here is the temperature map. So it's just one of the panels from the previous simulations, but it's the most dramatic one, you know, the one that was going poof and the blowing up, right? And you're going to see the differences between these simulations, particularly with these black holes. And this is the big difference between my simulation and all the others. Okay, let's take a look. So early on, of course, gas is still cold, not much going on. You know, you start to see this large-scale structure forming. Ooh, look at Simba. Blowing out those like bipolar jets, right? Boom, look at that. Crazy, right? This is Illustrious CNG. It looked really dramatic in that other movie. Hey, heck, nothing compared to this, right? Magneticum is also fairly dramatic. You know, these 2 are relatively mild. The key thing is that these things were bipolar. All these types of heating, you notice, were very spherical, like they're roundish, right? So this is the temperature map of what the Simba universe looks like today. You might think, my goodness, that's way different than anything else. Surely it would be easy to go out and measure something in the universe to tell us which one of these is right. Turns out, not so much, right? Because gas is hard to see, and especially measuring the temperature of really hot gas is very hard to see. Now, the key thing here, I want you to keep in mind, all these differences, all of these simulations produce the same set of galaxies in terms of their stars. Right? So despite all of these crazy differences, we've all tuned our models so that they get the same stars. Right? And you can get these huge differences, right? So essentially, what is the difference between these models? It's the way in which we've implemented all these kinds of physics processes, particularly all these feedback processes, which are the most uncertain, you know? And so that's why we have many, many groups doing this, because everybody thinks they're smarter than the next guy and or girl, and they're gonna basically do, you know, their model, and it's gonna work better than everybody else's, right? And that's the whole point. We're you know, we sort of all, you know, do our simulations, we come together, we have a few beers, we compare our runs, we compare to observations, we tell the observers they're wrong when they don't agree with our simulation, and then you know, we try to sort out which one is right, and maybe make some progress towards understanding whether the physics in this simulation is right or more right, or the physics in this one. And that's kind of how we do it, right? We kind of, you know, like a blind blind men and the elephant kind of thing, just kind of randomly walk. Okay, so you know, that sort of give you background on simulations. Let's talk a little bit more about the galaxies. I told you that we should understand these galaxies, right? Turns out Edwin Hubble wasn't just measuring distances and velocities and inventing cosmology, but he also started the field of galaxy. How did he do that? Well, of course, he started to view all these fuzzy blobs back in the 1920s, and not knowing what they were, the first thing he did was taxonomy. Right? That's always kind of, you start to try to classify things when you got a whole bunch of things. And he did notice that they classified into different types, right? Generally, they classified into elliptical galaxies and these things that are like spirally galaxies like this, right? Now, you might think of a picture of our Milky Way. You might have seen it. It looks something like this. Actually, it's categorized. It's an SBC, so right between SB and SC. That's where our Milky Way is. But you can see there are many other galaxies. Right? These are all real galaxies, right? So you can see they come in roundish shapes, kind of flattened oval shapes. They have these bars in the middle, so on and so forth. But in general, there's 2 classes, which are the ellipticals, the spirals. Now, all Hubble knew was the shape of the galaxy in the image that they could see. Yet, this classification system remains one of the most important and driving forces of understanding galaxy evolution, because to this day, we don't fully understand how all this comes about. Now, what did I mean by that? So, again, there's these two types of galaxies in the world, right? Very broadly. There's these elliptical galaxies, big, sort of formless, roundish blobs. Here's a nearby example called M87. And here's a nearby spiral galaxy, kind of vaguely an analog to our Milky Way, called M101. Now, if it was just the shapes that were different, you might think, who knows, one thing got a spiral, one thing got elliptical. But in point of fact, this shape corresponds to a huge number of other properties of these galaxies. And this is where things really get interesting, right? Because it turns out that whenever you see an elliptical galaxy, you'll find that it tends to be quite massive, tends to not be forming any new stars, right? So what happened? Why is it not forming any stars anymore? Whereas the spirals tend to be lower mass and tend to be forming a lot of stars, right? You can look at the Orion. If you've ever seen the Orion constellation, one of the stars on the belt, is the belt of Orion? The sword of Orion. Sword of Orion is actually a star-forming region. And so, there are new stars being formed in galaxies like the Milky Way. So you have only old stars here. Here you have younger stars and older stars. These galaxies are all red in color. These are blue. These have a lot of hot gas. These don't have very much hot gas, have much more cool gas. These tend to live in dense regions. There are a whole bunch of galaxies around it, right? Whereas these ones tend to be fairly off by themselves. There's very little dust in these. These are quite dusty, okay? And big clue, turns out, these tend to have very large black holes. In fact, the first black hole ever imaged with the Event Horizon Telescope was down in this galaxy right here at the center, M87. And you can even see, if you have good eyes, this little stream of material coming out, that's a jet coming out from the central black hole. Just like those jets that were in Simba coming out. We can't see the one on the other side for various reasons, but you can see it coming back. And with the Event Horizon Telescope, you can trace that all the way back down to that black hole itself. So clearly, the morphology of these galaxies is telling us that there is some big physics, right, that separates galaxies into these two populations. What could it be? So again, we can turn to simulations and try to understand how, what are the differences? We can go into simulation and look, there we formed a spiral. What did that look like? Over here on this galaxy, we formed an elliptical. What did that look like? Okay, so here's zooming into a particular region of the simulation, again, from Illustris, where we're going to end up with a spiral galaxy. Now, we're starting pretty late here. We're already starting about 4 billion years in, just to avoid the early times. You can see all the little galaxies flying around, right? You can see it's a very flattened disk. The colors of the stars, red means that it's older stars, right? Blue means it's a little bit younger. So you're going to see, all these stars like flying together. Here's just off the edge, a little spiral. See these galaxies are rotating disks. As you see the materials sort of collect onto the galaxies, you can see these star formation occurring in the outskirts of these galaxies, forming into these spiral arms, right? Like that. Hey, this is quite nice. All we did was put particles in a box and add a few equations, and we got this, right? So this is kind of cool, right? Looks a lot like a galaxy. It's going to have another little merger right here. Whoa, okay. That might be something like what's going to happen between the Milky Way and Andromeda in about 5 billion years. Okay, watch out for that. Again, it's going to end up in a somewhat more tightly wound spiral with a lot of old stars in the middle and the young stars on the outside, right? The young newly forming stars, right? So that's an example of how we can understand. Now, when we first started doing this, when I started doing this, in the late 90s, no one could form a spiral galaxy that looked like that. It required adding all of that physics, these feedback and supernovae and black holes and all of these things in order to form a spiral like that. So again, this is how we sort of do things. Let's now look at an elliptical galaxy, just for kicks and giggles, right? So this is the formation of a region of elliptical galaxy. We're going to start off in a larger region. Why? Because we need more mass. Ellipticals are more massive, so we're going to be have this sort of bigger region. So things are not as dramatic here because we're kind of looking at a larger chunk of space. But nonetheless, you're going to see this kind of the same kinds of processes. In particular, you're going to see that there's this big filamentary structure here. There's already a bunch of galaxies that are kind of interacting and coming together, right? There's galaxies coming up from here. There's some big thing over here that's clearly attracting everything up towards that region. But for some reason now that's going to turn around a little bit, and we're going to have the things start to collect together in a denser region. So now we're about maybe 3 billion years into the universe, and we're starting to collect together these sorts of galaxies. Now, early on, these galaxies are still spirals. It's really hard to see on the screen. It's much better. But some of these galaxies you can see little disks associated with them. You can see them kind of spinning around. And as they merge together, the merging process, as galaxies are drawn together with gravity, is very disruptive to this beautiful spiral disk, right? That's a very fragile pattern. When you throw things together, they tend to smear out all the patterns. When they smear out all those patterns, what are you left with? A big blob, right? And that's basically your elliptical galaxy. So here we go. We have, now we see all these mergers that are coming in. You see, there's still tons of galaxies around, right? This is what I was talking about, that these ellipticals tend to live in these dense regions. Why do they live in, dense regions? Oh, here comes a nice spiral coming in there. But again, that spiral structure is all going to kind of get disrupted and distorted and blown off because of all the tidal interactions that are sort of shredding it apart. And you end up with these very old blob of stars, which looks just like an elliptical galaxy, right? So we understand that elliptical galaxies formed because they live in dense regions. They had a lot of mergers. So even if they started with a whole bunch of spirals, they ended up, destroying all that spiral structure, forming a blob. And on top of that, they ended up, they had to have been in a dense region, right? They had to live in a dense region in order for that to happen. So again, these are the kinds of things you learn from these types of simulations, right? So in the last couple of minutes, I just wanted to point out what South Africa's role is in all this, okay? So I'm sure many of you are aware of the MeerKAT telescope out in the Karoo, right? It's been operating since 2022. It's a precursor to a much larger radio telescope that's going to be built out from MeerKAT, called the Square Kilometre Array, led by a consortium of countries based in the UK. Now, for galaxies, this radio data is going to do amazing things for lots of different fields, but for galaxies, there's two basic pieces of information that are huge for understand that we can't get any other way except by looking in the radio. And that's detecting this pervasive but very hard to see hydrogen gas. It turns out that hydrogen happens to have a transition at, it's a hyperfine forbidden transition. Forget about that if you don't know what that means. But anyway, the wavelength of that transition happens to be at 21 centimeters. That's very long. That's like the length of your hand. That's a single wavelength of that light, right? That's in the radio. And because of that, by looking in the radio, you can see all this hydrogen that you can't see any other way, right? And you can see that this tells us some very interesting things, particularly about the outskirts. Because remember, there's a lot of hydrogen out there. It's just hard to see. So we want to be able to see, what's between these stars, what's going on with all this craziness and stuff like that. I'll show you a movie in just a second. This is the optical region. This is what you see with your own, eyes or something. If your eyes were sensitive enough, you can see how much farther out you can see with the H1. So that's really cool. The second thing, which I've already talked about a little bit, so I won't mention anymore, are these black holes and these jets that are coming out of a black hole. This is a nice image from Centaurus A, which is a nearby elliptical galaxy with a big black hole. And again, these radio jets, they're called radio jets, in fact, and the reason they're called radio jets is because these jets are relativistic, and therefore they have a strong synchrotron emission. And it turns out that most, in most of the electromagnetic spectrum, that synchrotron emission is sort of overwhelmed by other, types of emissions, stars or dust or whatever. But once you get out to the radio, nothing else is emitting in the radio. So you can actually see the synchrotron emission. And that gives you these beautiful radio lobes. It's the radio image here, right? So you can directly trace these kind of jets, which seem to be so important for doing all these, heating of the gas, so on. So that's really cool, right? And particularly this idea of this probing this cosmic ecosystem, I think is the next big frontier in galaxy formation, or really the current frontier in galaxy formation. So just to give you an idea, again, we've seen a simulation like this, but just to emphasize it, right? Galaxies are not serene, isolated objects, right? So here's a forming galaxy. It's going to end up with a galaxy much like the Milky Way. This green stuff that you see, or anything that's in green, is stuff that you could probably see in neutral H1, right, in the radio, if you had a sensitive enough telescope. Okay, so you can see that there's supernovae going off, there's things being blown up, there's mergers, there's gas streaming in, all these kinds of things are going on in the simulation. But if we could actually see all this stuff, instead of the only things we can see is the little tiny disk of stars down inside there, if we could directly see all of this stuff, right, that's a hugely powerful view of this cosmic ecosystem in which these galaxies are growing and evolving, right? And this is the kind of thing that H1 21 centimeter in principle will allow us to do. And this is why, we've spent so much money. South African government has spent so much money to try to will build the world's best radio telescope, right? One of the many reasons. So now you're seeing it settle down into a nice, beautiful disk-like thing. Okay. All right. Well, that's basically all I wanted to say. I think hopefully you've enjoyed the movies. All right. These simulations are a linchpin, really, to helping understand the origin of the universe and to understand this question of why the universe looks the way it does, right? This scientific version of our cosmic origins. And so, they've revealed how the galaxies that we see can emerge from this very primordial soup of a very smooth distribution of very hot gas through the processes of gravity and many other things, many other physical processes from a range of scales. And I think solving this is really one of the great challenges in 21st century physics, to understand all the processes that are needed to make these kind of galaxies. And we made huge progress, I say, in the last 15, 20 years. From when I first started with simulations, it was kind of one of these things that, look at your cute guy doing simulations, the little cute things. Nobody paid any attention to us, right? We were like, because we couldn't even produce a real disk galaxy. Like, it's like, okay, come back when you can actually produce a Milky Way, right? Well, it took us about 15 years, but now we can do it, right? But it took a lot of work. So, so this is there's a lot to be done yet, but I think we made a huge progress, and it's going to be a very exciting next few years in this field. Thanks.
Thanks, Romeel, for that excellent presentation. We've got time for a couple of questions. Do we have any questions from the participants online? Nothing.
No questions online.
Okay, great. How about the people in the audience?
This might be a very stupid question, but is it possible to create a model of the universe, a kind of simulation that's real life, replace stars with particles, scale things down? Is that something that's possible?
Yes. So people have tried to do that. The problem in simulations is always one of dynamic range, that we want to resolve all the small scale, beautiful features, of galaxies, but we wanted to do it in a representative volume. And so modeling them both together is difficult. So one way that people try to do this is by replacing galaxies with sort of point particles or stuff like that. I think that's still sort of early on, because people are kind of interested in galaxies themselves, like why are they spirals and stuff, and if you just have them as a point, then you don't get any of that information. So yes, but I would say that it hasn't really taken off just yet.
Hello.
Why does the SIMBA simulation produce jets and the other ones do not? You never told us what makes SIMBA so special.
Because I put it in, right? So we all have to make these choices as to how we implement these models. So I took a look at some of those radio galaxies with those big jets and go, well, clearly they're putting out stuff in this direction, right? In these bipolar strong jets. Turns out it's very difficult to get galaxies to work doing that. So most people kind of gave up on that. And it's much easier if you distribute the energy spherically, which is what all the other simulations do. And the reason for that is basically the whole point of the main, what do you call it? The main outcome of this black hole feedback is to shut off the star formation. Remember, I told you that the spirals are forming stars, the ellipticals are not, right? Yet the ellipticals are bigger, so they should have a lot more gas, but they're not forming stars. Why is that? Because the black hole, the energy of that, has cleared out the gas. Now imagine you're trying to take a ball of gas and you're trying to clear it out. Well, if you put the energy only in this direction, it'll clear out the gas in this direction, but what about all the gas over here? Won't do much to it, right? That's what makes it difficult. So in order to overcome that and to be able to produce these sort of quenched elliptical galaxies, they sphericalize the energy in. But my thinking was that the universe somehow does this, right? So we have to figure out what the universe actually does, not, you know, the simplified version that gets our code to work. So this was my logic for putting it in. The flip side of that is because of that, we had to put a lot more energy in order to clear it out, right? Which is why we ended up with so much hotter gas at the end. So that was the trade-off. But the point is, like, there aren't obvious, any obvious observations that rule out SIMBA's model at this point, right? There are some that favor other models or some that favor SIMBA. Kind of a mixed bag.
Sorry, I have a quick question about the box of the simulation. Should we consider the periodic boundary condition? Okay, the particle disappear from one side, reappear from another side. Mm-hmm.
Yes, that's generally we have periodic boundaries assumed in this.
Thanks for a great talk, Romeel. Do any cosmological simulations consider non-Newtonian types of gravity?
So people have tried to do simulations with MOND. That's, of course, the most famous type of non-Newtonian gravity. The big problem with MOND is that the potential is not converged. So on large scales, it goes to 1 over r, not 1 over r squared, which means the integral of that is, you know, if you try it, is not going to work. Right? So the upshot of it is to do a representative volume, you need a huge volume, right, to actually get enough to converge. There are about, you know, 1,000 other reasons to rule out MOND at this point. So it doesn't seem, yeah, so there hasn't been a huge amount of effort in it, but people have done it. Yeah, there's certainly, you know, people who have done, you know, lots of simulations with varying dark matter, and so forth. Yeah.
So thanks for the interesting talk. So you mentioned that a lot of work has been done in the last 30 years. That of course true, but another point is of course that the computers have become much more powerful in very same period of time. So by how many orders of magnitudes have the numbers of particles that you can put into the box increased?
Yes, good question. So that's right. And in fact, you know, I wouldn't say that all the progress has been purely because we're smart. It's a lot of it is because computers are bigger and there's a huge gaming industry that helps us get a lot faster computers, right? But to answer your question, so at one point in time, I actually ran the world's largest simulation. It took about 8 months on the Illinois NCSA supercomputer back in the late 90s. And that had a number of particles. What is it? It's something like 30,000 particles. Today, I've been running that on my little desktop server overnight. Okay, I use that as a little, not that particular one, but that size simulation as a test simulation. Today, we are now reaching simulations that have trillions of particles. So this is, whatever that is, that's about 10 to the 5, 10 to the 6 times bigger. So that's been the progress since the 1990s, in the computing power. So it's a combination of also just raw fast computers, but also algorithms. So we've developed a lot of algorithms to speed things up. We use a lot of parallelization, a lot of so on and so forth, optimization, etc. So yeah, we're sort of we have to have one foot in computer science at all times because we don't drive the industry, but nonetheless, whatever is the latest industry thing, we should think about trying to take advantage of it because that's where all the money's going to go and that's where all the cheap hardware is going to be. But like GPUs, like a lot of people are interested now in using GPUs. Very difficult to port these kinds of codes to GPUs, but it's happening.
I've got two questions. So my first question is, do you guys, for most of these simulations, do you still use older languages like C, or have you started moving to newer languages like Rust that make parallelization easier? And then second question is, in your simulations, is a particle a literal particle like a hydrogen particle, or is it like a clump of hydrogen? Or like what size scale are we talking about when you talk about a particle?
Yeah, good question. So the answer is most of these codes are still written in C, and even some horribly that should be took out back and shot in Fortran. So that's, I think it is true that there are codes these days to make things more easily parallelizable and stuff, but a lot of this is legacy code. But also, it's not that difficult. Compared to like some kind of big thing that Microsoft would write, it's not that difficult code to write. It is for us because we don't know computer science, but it's really more about the physics and stuff like that. So that's not really a bottleneck, but we mostly use C because we want every inch of speed, right? The particle size is a good question. So yes, the idea is this is a chunk of the universe. The typical chunk mass, very ballpark, about 1 million times the mass of the sun. Okay, so that means we're not going to resolve individual stars, and make little tiny constellations, stuff like that, right? Each particle represents 1 million solar masses. So one might think of it as, if you're familiar with that, something like a globular cluster or a big cluster or something like that.
If I can ask, do those interact like clumps of gas or solid objects, or?
Yeah, so they interact. So again, we have the gravitational force. The gravitational force has what we call a softening, and that's to avoid the fact that gravity is 1 over r squared. So r being the distance, right? So if the two things end up at the same point, which they can due to machine precision, the thing will blow up, right? So as a result, we soften the gravity. For the hydrodynamics, we do something a little different, which is to basically, have, but a similar idea. We have a smoothing length. So one would think of each gas particle as not a single point of gas of that mass, but rather gas spread over some region of space with some particular profile. And that's how and we write down all the equations to account for that.
Thank you.
We've got some questions from the online viewers.
Yes, we've got 3. There's one hand up. We need to give him access to talk, but I'll read the other 2 quickly first. So the first question here is there any MOND or MOND model that simulates our universe?
As far as I know, not on large scales. There is structure formation that you see in those simulations, an extremely accurate test of the law of gravity. and it's very difficult to produce that if you deviate much from 1 over r squared. The way that pattern evolves over time, and that's something that's now been observed extremely well. So it's very difficult. MOND is very successful at producing, for instance, the individual rotation curves of galaxies. But there are other ways to explain that as well. So that's really what MOND was designed to do. The problem with MOND is it only works well in that one regime. Anywhere else we do with it, we look at it, our standard cold dark matter model works much better.
Okay, and the other one is, you mentioned dynamic range. Does the cosmological zoom-in n-body simulation approach help to probe small scales much better? What is your opinion on the cosmological zoom-in n-body simulation approach?
I love zoom simulations. In fact, that last simulation I showed you from the FIRE group, that was a zoom simulation. So just for the rest of you, the idea is, okay, we have a problem, getting fine details because we have these, million solar mass particles. But what happens if we sort of take one of these large simulations and we extract out one particular region and we just simulate that region with really, really much, much finer particles, right? And then we can get much more detail. Okay, we only get it on like one galaxy. Okay, fine, as opposed to, thousands. But we can study these sort of detailed processes, and that's extremely effective, right? The two approaches are very complementary. So one of the things that we did in Simba, actually we did it in its precursor simulation, Mufasa, was to partner with the Zoom simulation people. Now the Zoom simulation people are doing all this physics much more accurately than we can do it, because we have these very coarse resolution. We can't do it very accurate. They can do it much more accurately, and we can ask them, like, what if you took your simulation, your beautiful simulation, and blurred it out to look like one of our simulations, right? Coursed it up to look like one of our simulations. What kind of results would we get? And could we put that information to our simulation? And so we have a connection between the small scales, and we take the information directly from the small scale simulation, Zoom simulation, and put it into ours. And so I think we were one of the pioneers of trying to do this. Still, we're one of the only ones who really do this very commonly. And we've done that for both the black holes and the stars, feedback and all that kind of thing. So yeah, it's a very powerful technique, and something that's definitely a big part of what we do.
Okay, Martin, you have the right to speak. You can go ahead, please.
Thank you very much. This was a very, very, very interesting talk. Just something I would like to know. In you ran 2 simulations, one for the formation of a spiral galaxy and the other for an elliptical galaxy. Right. How does one know the starting conditions that one requires in each of those 2 simulations?
Right. So what we actually do, right? Well, I didn't actually do that. That was done by the illustrious TNG group in that particular case, the movies I showed. But although we have done similar things, is we first run one of these big simulations, just pure cosmological simulations. And then, again, it's sort of like this Zoom technique. We say, okay, I know, according to this cosmological simulation, by the end, I know this galaxy is going to be an elliptical. So let's just look at that one in more detail, right? So then you can sort of rerun it with this Zoom technique into this more high resolution region. So in a sense, we start with the exact same initial conditions given to us by the cosmological simulations, which originally come from these cosmic microwave background measurements, right? These tiny fluctuations. So that's really the starting point for all of these simulations, whether it's a Zoom or not, right? That's the thing we know to start from. So it's not really any different in terms of that. It's just, where do we put the computational effort? Do we put it in, running many particles over a huge volume, or do we put it into running a small volume with a large number of particles?
Okay, thank you very much.
Okay, I think that's about all the time we have for questions today. It was a very thought-provoking presentation. Before I invite the physical